Let's solve one last closed system problem before we move on to open systems. And this one will involve air as an ideal gas being used in a cycle. Air contained in a piston cylinder assembly undergoes the power cycle shown. Assuming ideal gas behavior for the air, evaluate the thermal efficiency of the cycle. So we have three processes in series that form a cycle. The cycle ends where it begins at state 1. The first process is an isothermal process. The second process is a constant pressure process. And the third process is a constant volume process. Let's lay out our storyboard for this problem. We always begin with a schematic. We have a piston cylinder assembly containing air, and we will define the air as the system which we are evaluating. The given data defines the pressure and specific volume at each of the three states, which were taken from this diagram. And we also describe the three processes for this cycle, the first being isothermal, which is a polytropic process with the value of n equal 1. Process 2.3 is isobaric, and process 3.1 is isovolumetric. We'll create an engineering model for this cycle. Clearly, we have a closed system. We'll ignore any changes in kinetic or potential energy, which are probably truly zero anyway, and we'll treat air as an ideal gas. And what we are asked to find is the thermal efficiency of the cycle. In order to calculate the thermal efficiency, we're going to need to calculate first the work and heat transfer term for each process. And of course, the work and heat transfer are given in terms of energy per unit mass. So let's look at the first process, an isothermal process. We know that always work is the integral of P dV. And for an isothermal process, which is a polytropic process for n equal 1, we have previously evaluated that integral expression as P1V1 times the natural log of V2 over V1. Well, all of these values are known to us. We can plug them into this expression. We'll convert bar cubic meters to kilojoules, and we find that work for process 1,2 is 804.7 kilojoules per kilogram. Now we can use energy balance on process 1,2 to find the heat transfer. We can write that the delta U is just Q minus W, all of these terms for process 1,2. And we're using, notice that we use a small u, a small q, and a small w, indicating that those expressions have been divided by the mass. We also know that in this first process, which is described as isothermal, T1 is equal to T2, and therefore delta U is 0. This is true because temperature and internal energy both measure in different terms the molecular activity of the substance. So with delta U equals 0, we have 0 equals Q minus W, or just Q equals W. So for process 1,2, Q will equal what we previously calculated as the work term, which is 804.7 kilojoules per kilogram. Let's move on to the second process, which is a constant pressure process. And we have previously resolved the PdV integral for an isobaric process. It's just the pressure times the change in specific volume. Again, plugging in those values and converting bar cubic meters to kilojoule, we found that the work for process 2.3 is minus 400 kilojoules. Now, we can find the values of internal energy in the air table if we first know what the temperatures are. And we're going to need the temperatures of state 2 and state 3 in order to do that. So we can rearrange the ideal gas law. It's just the temperature is equal pressure times specific volume divided by the gas constant. So at state 2, we have a pressure of 1 bar, a specific volume of 5 cubic meters per kilogram. I have an energy unit conversion term here. divided by the gas constant, which is the universal gas constant divided by the molecular weight. And I calculate that T2 is 1742.2 degrees Kelvin. We'll do exactly the same thing for state 3, and we calculate that T3 is 348.4 degrees Kelvin. I'm going to digress here for a moment and show you that we could have calculated T3 in another way. With the ideal gas law, we can always put the constant variables on one side of the expression, and in any process, we can write that P2V2 over T2 is equal to R, which is also equal to P3V3 over T3. Now, in this particular case, P2 is equal to P3. It's a constant pressure process. So for this particular process, V2 over T2 is equal to V3 over T3. I can rearrange this and say that T3 is T2 times V3 over V2. I know all of those values. And so I calculate T3 as exactly the same value as we did in the previous method. Now that we have the temperature, we can go into the air tables and get a value for internal energy. But of course, we don't have a value for 1742.2 K in the air tables. It's somewhere between 1700 and 1750 K. So we're going to interpolate, and I'm not going to show the details here as I have in the past of the interpolation process. But I'll simply show you the result. U2 is 1432.5 kilojoules per kilogram. And we'll do exactly the same thing at state 3. We know the state 3 temperature, and we find it sitting between 340 and 350 degrees K. We'll interpolate and again get a value from the table. U3 is 248.9 kilojoules per kilogram. Well, now that we have that, we can write an energy balance for process 2.3, and that's just Q is delta U plus W. And delta U for process 2.3 is written as U3 minus U2. And we have those values, so we can plug them in. We already calculated the work for process 2.3 as minus 400 kilojoules per kilogram. So the heat transfer for process 2.3 is minus 1583.6 kilojoules per kilogram. And now for our third process, process 3.1, which is an isovolumetric process. We know that the work can be stated as the integral of P dV, but in an isovolumetric process, dV is 0. So the work for this process is 0. Now let's calculate the value of heat transfer by the energy balance. We know that U is Q minus W, but when W is 0, we just have that Q for process 3.1 is simply U1 minus U3. Now we noted earlier that state 1 and state 2 had the same temperature. And we also noted that therefore the internal energy at both states must be the same. Well, we know that the value of U2 is 1432.5 kilojoules per kilogram. Therefore, the value of U1 is the same. Knowing that, I can say that Q for process 3.1 is U1 minus U3. We previously determined the value for U3, and so I know everything I need to calculate the heat transfer for this process, and it's 1183.6 kilojoules per kilogram. Let's summarize all our calculations to date. We have 3 processes, and we have calculated the work and the heat transfer per unit mass for each of the 3 processes. Let's sum those. Let's sum all the work terms and sum all the heat transfer terms. And notice that they are identical, both sum to 404.7 kilojoules per kilogram. Well, it is necessary that they do so. Remember that a cycle ends where it begins. And so the change in energy during a cycle must equal 0. And if delta E is equal to 0, well then Q has to equal W. And we can see for this cycle that they do. Now let's calculate the thermal efficiency. The thermal efficiency is simply what we want from the process, which is the power output. divided by the heat we transfer into the cycle. So the net work is simply the sum of all the work terms, which we've already summed here. But the heat that we put into the cycle is only the heat transfers that are positive. So positive Q is energy transferred into the cycle by heat transfer. A negative time is energy rejected to the low temperature thermal reservoir by heat transfer. So for Qn, we're only going to put in our positive terms, which are Q for process 1,2 and Q for process 3,1. So putting these values in our expression for thermal efficiency, we get that the thermal efficiency is 20.4%.